Mathematical equations can look intimidating at first glance. Symbols sit quietly beside one another. Letters mingle with numbers, and strange shapes seem to whisper secrets in a language few people fully understand. And yet beneath that surface complexity, equations are remarkably calm. They are not chaotic scribbles. They are careful compressions of thought. Each one is a small, elegant story about how something in our universe behaves. Tonight, we will explore some of the most unusual equations ever written, not to memorize them, not to test ourselves, but simply to observe them slowly, to let them unfold in a quiet and reflective way. There is something subtly powerful about understanding an equation, even just a little, when you recognize that E equals I times pi plus 1 equals 0 is not random, but a gentle connection between 5 fundamental constants. It changes the way the symbols feel. They soften, they begin to seem less like barriers and more like windows. Equations are compressed worlds. A few characters can describe the spread of heat through metal, the motion of waves across an ocean, or the curvature of space itself. They take something vast and distill it into something still. Take a moment to imagine each equation not as ink on a page, but as a landscape. Lines curve. Values rise and fall. Patterns repeat quietly. Beneath every symbol is structure. Beneath every structure is relationship. As we move through these unusual equations together, allow yourself to slow down. There is no rush to understand everything. Simply notice the harmony, the symmetry, the hidden order. Mathematics does not demand urgency. It invites patience. And in that patience, something unexpectedly soothing begins to emerge. Before we continue, if you like these types of deep thinking videos, please take a moment to subscribe and like so that we know that the YouTube algorithm is sharing the videos to the right people. Thanks. Euler's identity is often described as the most beautiful equation in mathematics. At first glance, it appears almost mysterious. It says that e raised to the power of I times pi plus 1 equals 0. Written in symbols, it looks compact and almost cryptic. But when spoken slowly, it becomes something softer. It says that a special number, called e, when raised to an imaginary exponent involving pi, produces -1. And when we add 1, everything balances perfectly to 0. Take a moment to notice what is present in this single relationship. There is e, the base of natural logarithms. This number is approximately 2.71828. It appears whenever growth happens smoothly and continuously. It governs compound interest, population growth, radioactive decay, and the gentle accumulation of change. It is the quiet rhythm of exponential increase. There is pi, approximately 3.14159. Pi is the ratio of a circle's circumference to its diameter. It appears whenever curves, rotations, or waves are involved. It connects straight lines to circles, motion to geometry. There is I, the imaginary unit. It is defined as the square root of -1. At first, this seems impossible. How can a number multiplied by itself produce a negative value? For a long time, mathematicians were uneasy about this idea, but eventually they accepted that extending the number system allowed deeper consistency. The imaginary unit does not break mathematics, it expands it. And then there are the simplest numbers of all, 1 and 0. 1 represents unity. 0 represents balance, nothingness, completion. What makes Euler's identity so unusual is that it brings all of these together: growth, rotation, imagination, unity, and nothingness, all in one gentle statement. To understand why this works, imagine a circle centered at the origin of a coordinate plane. Instead of thinking about numbers only on a straight line, picture a flat surface where horizontal movement represents real numbers and vertical movement represents imaginary numbers. When we raise e to larger and larger real powers, the result grows steadily along the horizontal direction. But when we raise e to imaginary powers, something different happens. Instead of moving outward endlessly, the values begin to rotate around the circle. Multiplying by I corresponds to a quarter-turn rotation. Multiplying by pi adjusts the angle precisely halfway around the circle. So when we raise e to the power of I times pi, we are not stretching outward, we are rotating exactly 1/2 turn, and a half turn on a circle brings us to the opposite side. On the real axis, that opposite point is -1. So e raised to the power of I times pi equals -1. And when we add 1, the result is 0. It is not chaos. It is rotation disguised as exponentiation. Take a moment to visualize this movement. Imagine standing at the point 1 on a circle. Now gently rotate halfway around. You arrive at -1. The journey is smooth, continuous, calm, no sudden jumps. Just steady motion guided by invisible structure. What feels surprising is that exponential growth, which we usually associate with rapid increase, is quietly connected to circular motion. Growth and rotation are not separate ideas. They are reflections of a deeper unity. There is something profoundly calming about that. Euler's identity suggests that concepts we think are unrelated are actually intertwined. Algebra meets geometry, real numbers meet imaginary numbers, growth meets symmetry, and all of it resolves to 0. Not as destruction, but as balance. Philosophically, this equation whispers something subtle. It reminds us that opposites can harmonize, that complex movement can return to stillness, that even the imaginary has a structured place within reality. It also humbles us. For centuries, these constants were studied separately. Pi in geometry, E in calculus, I in algebra, yet they were waiting quietly for someone to see the bridge connecting them. When Leonhard Euler first wrote this relationship in the 18th century, he likely did not describe it as mystical. He was simply following logical consequences of infinite series expansions. If we expand e raised to a power into an infinite sum of fractions and carefully substitute I times pi, the pattern simplifies step by step. Terms cancel gently. Real and imaginary components settle into place, until finally -1 appears. The path is technical, but the destination feels almost poetic. Even if we do not follow every algebraic detail, we can appreciate the structure. 5 fundamental constants. 1 compact expression. Perfect balance. There is also a quiet confidence that comes from understanding even a fragment of this equation. When you recognize that it encodes rotation, growth, and symmetry all at once, the symbols begin to feel less intimidating. They feel like shorthand for something elegant. Take another slow breath and imagine the circle again. Imagine exponential curves blending into arcs. Imagine numbers extending into new dimensions without breaking consistency. Mathematics often expands by allowing what once seemed impossible. Negative numbers were once controversial. Imaginary numbers even more so, yet each extension created a more complete system. Euler's identity stands as a gentle monument to that expansion. It tells us that reality may be broader than intuition suggests, that strange ideas can fit together with surprising grace, that beneath abstraction lies coherence. As you let this equation settle in your mind, notice its symmetry. Notice how it begins with complexity and ends in simplicity. E raised to the power of I times pi plus 1 equals 0. A quiet cycle. A half turn. A return to balance. And perhaps that is why so many people find it beautiful. Not because it is flashy or loud, but because it unites distant ideas in a calm and inevitable way. In the end, Euler's identity is not just an equation. It is a reminder that mathematics is capable of weaving together growth, motion, imagination, and stillness into a single, harmonious whole. And that harmony, once seen, feels surprisingly peaceful. The Basel problem begins with a simple question. What happens if we take 1 divided by 1 squared and add it to 1 divided by 2 squared, and then add 1 divided by 3 squared, and continue this pattern forever? At first it seems harmless. 1 over 1 squared is just 1. 1 over 2 squared is 1 over 4. 1 over 3 squared is 1 over 9. Each new term becomes smaller and smaller. The fractions gently shrink as the denominator grows. So the question becomes this: if we continue adding these shrinking fractions forever, does the total grow without limit, or does it settle toward a specific number? This type of expression is called an infinite series. It is not a sum with a final term. It continues without end. But even without an ending, some infinite series approach a stable value. They grow more and more slowly, inching toward a limit, like a quiet river approaching still water. The Basel problem asks for the exact value of this infinite sum, 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 3 squared, and so on, continuing endlessly. For many years, mathematicians tried to determine its value. They could calculate partial sums. Adding the first few terms gives a number a little larger than 1. Adding more terms pushes it higher, but each addition contributes less than the one before. The growth becomes gentler, almost hesitant. Eventually, in the 18th century, Leonhard Euler discovered something remarkable. The infinite sum equals pi squared divided by 6. Take a moment to let that settle in. We begin with fractions built from whole numbers. There are no circles, no geometry, just arithmetic. Yet somehow the result contains pi, the number that describes circles, the sum of 1 over n squared, from n equals 1 to infinity, equals pi squared divided by 6. Why should a problem about counting squares of whole numbers produce pi? At first glance, it feels unexpected, even mysterious. But as with many unusual equations, the mystery softens when we explore the hidden structure beneath it. To understand why this happens, imagine plotting the function 1 over x squared on a graph. As x increases, the curve drops smoothly towards 0. It never touches 0, but it approaches it gently. If we were to calculate the area under this curve from 1 to infinity, we would find that the area is finite. The curve falls quickly enough that the total accumulated area does not explode. This connection between infinite sums and areas beneath curves is one of the central ideas of calculus. Discrete additions and continuous shapes are quietly linked. Euler approached the Basel problem by examining the sine function. The sine of x is deeply connected to circles and therefore to pi. It turns out that the sine function can be expressed as an infinite product involving its zeros, the points where it equals 0. Those zeros occur at multiples of pi. By comparing two different ways of expressing the sine function, Euler noticed that the coefficients must match, and hidden inside that comparison was the infinite sum of 1 over n squared. Through careful reasoning, he uncovered that the sum equals pi squared divided by 6. The appearance of pi here is not random. It reflects a deeper unity between arithmetic and geometry. The squares of whole numbers are not isolated objects. They connect through infinite patterns to circular motion and trigonometric waves. Take a moment to visualize the fractions themselves. 1, 1/4, 1/9, 1/16. Each term is smaller than the last. They fall away gently, like echoes fading into silence. And yet, even as they shrink, they contribute something essential to the total. The total does not wander unpredictably. It settles near a specific value. Pi squared divided by 6 is approximately 1.644934. Notice how calm that number feels. It is not enormous. It is not chaotic. It is modest and precise. There is something soothing about infinite processes that converge. They suggest that endlessness does not always mean disorder. Infinity can approach stability. Growth can approach balance. The Basel problem also reminds us that intuition can be limited. If someone had asked centuries ago whether adding the reciprocals of squared numbers would produce pi, most would have said no. There is no obvious circle in 1 over 3 squared, and yet mathematics reveals that hidden pathways exist. Philosophically, this equation invites reflection. It shows that patterns extend beyond their immediate definitions. Whole numbers, squares, infinite sums, trigonometric waves, and circles are woven together in ways that are not immediately visible. It also shows the power of persistence. The problem was posed in the 17th century in the city of Basel. Many brilliant minds tried and failed to solve it. When Euler finally succeeded, it was not through brute force but through creative connection. He looked at familiar functions in a new way. The solution did not destroy mystery, it deepened it. Imagine again the series stretching into infinity, term after term, smaller and smaller. You never reach the end, and yet you approach something definite, a boundary that is never crossed but endlessly approached. This mirrors many processes in life: effort that accumulates slowly, change that stabilizes over time, motion that quiets into balance. The Basel problem is not dramatic. It does not shout. It whispers something subtle. That beneath simple arithmetic lies geometry. That infinity can be gentle. That distant areas of mathematics communicate silently with one another, and perhaps that is part of what makes understanding it feel quietly impressive. When you mention that the sum of 1 over n squared equals pi squared divided by 6, it sounds surprising, but behind that surprise is a serene structure. The fractions shrink, the curve falls, the sine waves oscillate, and somehow everything aligns. Take one final moment to reflect on the unity present here. A simple question about adding fractions opens into the geometry of circles and the behavior of waves. What seemed like pure arithmetic reveals curvature, and in that revelation there is something deeply calming. The golden ratio begins with a simple question about division. Imagine taking a single-line segment and splitting it into two parts, but not just any split. The division must satisfy a very particular condition. The ratio of the whole length to the longer part must be the same as the ratio of the longer part to the shorter part. At first, this sounds abstract, so let us slow it down. Picture a line. The entire line has some length. You divide it into a longer section and a shorter section. Now compare two relationships. First, compare the whole line to the longer section, then compare the longer section to the shorter section. The golden ratio appears when those two comparisons are exactly equal. When we translate this relationship into numbers, something remarkable happens. The ratio turns out to be equal to 1 plus the square root of 5, all divided by 2. Spoken gently, it is 1 plus the square root of 5, divided by 2. The square root of 5 is approximately 2.236. Adding 1 gives approximately 3.236. Dividing that by 2 gives approximately 1.618. So the golden ratio is about 1.6180339. It is an irrational number, meaning its decimal expansion continues forever without repeating. The digits extend endlessly, like a quiet stream that never quite finishes flowing. What makes this ratio unusual is not just its numerical value, but how often it appears. Consider a rectangle whose longer side divided by its shorter side equals the golden ratio. If you remove a square from that rectangle, the remaining smaller rectangle has the exact same proportions as the original. The shape repeats itself. The pattern echoes inward. This property is called self-similarity. The structure looks the same at different scales. There is something calming about that repetition. A sense that growth does not distort form but preserves it. Now imagine constructing squares inside the rectangle, each time removing the largest possible square. If you draw quarter circles inside each square, a spiral begins to emerge. This spiral expands outward in a smooth, balanced way. Although this spiral is an approximation, it resembles patterns found in nature. The arrangement of seeds in a sunflower, the spirals of certain shells, the branching of trees. These patterns are not exact manifestations of the golden ratio, but they often approximate it closely. Why should this particular number appear in living structures? One explanation lies in growth efficiency. When elements are arranged in proportions close to the golden ratio, they can distribute themselves evenly without overlapping too much. In plants, this can maximize exposure to sunlight or rainfall. But beyond biological explanations, there is something aesthetically compelling about the proportion itself. Artists and architects throughout history have been fascinated by it. Some claim it appears in ancient temples and classical paintings. Whether intentionally or not, the proportion tends to feel balanced to the human eye. Not too stretched, not too compressed. There is a subtle harmony in 1.618. The golden ratio is also deeply connected to a famous sequence of numbers known as the Fibonacci sequence. This sequence begins with 0 and 1. Each new number is created by adding the two previous numbers together. So it continues. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. As the numbers grow larger, something interesting happens. If you divide one Fibonacci number by the one before it, the ratio gradually approaches the golden ratio. 13 divided by 8 is 1.625. 21 divided by 13 is approximately 1.615. 34 divided by 21 is approximately 1.619. Each step moves closer to 1.618. The sequence does not begin with the golden ratio, but it grows toward it. This gradual approach mirrors the idea of convergence we explored earlier. A process unfolding step by step, drawing nearer to a hidden constant. There is something peaceful about that steady movement toward balance. The golden ratio also solves a simple quadratic equation. If we let the ratio be represented by the letter phi, then phi squared equals phi plus 1. Spoken gently, the golden ratio squared equals the golden ratio plus 1. This relationship captures its self-repeating nature. When you multiply it by itself, you simply add 1. It grows, but in a controlled and predictable way. Take a moment to imagine that. Growth that preserves proportion. Expansion that maintains harmony. Philosophically, the golden ratio suggests that balance is not always symmetry. It is not a perfect half-and-half division. Instead, it is an unequal division that feels stable. The larger part is about 1.618 times the smaller part. There is dominance, but not excess. Difference, but not imbalance. In life, many systems thrive not in perfect equality, but in proportional harmony. The golden ratio becomes a metaphor for that subtle equilibrium. There is also something intriguing about its endless decimal expansion. 1.61803398887498948, and so on. The digits continue infinitely without repeating, yet the overall proportion remains constant. It reminds us that complexity can exist within stability, that beneath endless variation lies consistent structure. When you mention the golden ratio in conversation, it carries an air of quiet sophistication. It connects geometry, algebra, art, biology, and number theory in one elegant proportion. But beyond sounding impressive, it offers something more calming. It shows that simple rules can produce patterns of lasting beauty. That division can create unity. That growth can follow a gentle rhythm. Imagine the original line segment again. Divided carefully, the whole relates to the part in the same way the part relates to the smaller piece, a chain of proportional relationships extending inward without distortion. There is no abruptness, no harsh edges, just continuity. The golden ratio invites us to look for harmony not in perfect sameness, but in structured difference. It suggests that beauty can arise from specific numerical relationships hidden beneath surfaces, and as we let this proportion settle into our thoughts, we notice something subtle. A simple act of division reveals a constant that echoes through mathematics, nature, and art. What began as a line becomes a spiral. What began as arithmetic becomes aesthetics. And in that quiet transformation, there is a sense of order that feels both unusual and deeply reassuring. The imaginary unit begins with something that once seemed impossible. For a long time, numbers were comfortable and familiar. Positive numbers counted objects. Negative numbers represented debt or direction. Fractions described parts of a whole. Even irrational numbers, like the square root of 2, could be understood as lengths on a line. But then a simple question appeared. What number, when multiplied by itself, equals -1? If we take 1 and multiply it by itself, we get 1. If we take -1 and multiply it by itself, we still get 1. Any real number multiplied by itself produces a positive result. So how could any number squared equal -1? For centuries, mathematicians encountered equations like x squared plus 1 equals 0. Rearranged, this becomes x squared equals -1. There was no solution among the real numbers. Rather than abandon the equation, mathematicians made a bold and quiet decision. They defined a new number. They said, let us call the square root of -1 by a new name. Let us call it I. The imaginary unit is defined as the square root of -1. At first, The word imaginary sounds dismissive, as if the number is less real than others. But over time it became clear that this new number was not an illusion. It was an extension, a widening of the number system. Take a moment to imagine the number line you learned as a child. It stretches endlessly to the right with positive numbers and endlessly to the left with negative numbers. Every real number lies somewhere along that horizontal line. Now imagine adding a vertical dimension. Instead of only moving left and right, you can now move up and down. The horizontal direction represents real numbers. The vertical direction represents imaginary numbers, multiples of I. If you move 1 unit upward, you're at positive I. If you move 1 unit downward, you're at negative I. This creates what is called the complex plane. Each number now has 2 parts, a real part and an imaginary part. For example, 3 plus 2i means 3 units to the right and 2 units upward. Suddenly, numbers are no longer confined to a single dimension. They occupy a flat surface. This expansion may seem abstract, but it unlocks something profound. Consider multiplication by I itself. If you multiply any number by I, you are effectively rotating it 90 degrees counterclockwise on this plane. Start at a number 1, located 1 unit to the right on the real axis. Multiply by I and you arrive at I 1 unit up. Multiply by I again and you arrive at negative 1, 1 unit to the left. Multiply by I once more and you reach negative I, 1 unit down. Multiply by I a 4th time and you return to 1. Multiplying by I is not random, it is rotation. 4 rotations bring you full circle. This reveals something deeply calming. The imaginary unit encodes movement. It transforms algebra into geometry. Instead of thinking about square roots of negative numbers as strange artifacts, we can think of them as directions, as rotations, as structure in motion. The imaginary unit also allows us to solve equations that were previously unsolvable. The equation x squared plus 1 equals 0 now has 2 solutions, positive I and negative I. What once appeared as a dead end becomes complete. There is a philosophical softness here. Sometimes, when a system feels limited, the answer is not to reject the problem, but to expand the system. The introduction of E did not break mathematics. It made it more consistent. In fact, once complex numbers are accepted, many areas of mathematics become simpler. Electrical engineering uses complex numbers to describe alternating currents. Quantum mechanics relies on them to describe wave functions. Signal processing depends on them to analyze frequencies. The imaginary unit quietly powers modern technology, and yet its definition remains simple: a number whose square equals negative 1. Take a moment to sit with that idea. A rule that once seemed contradictory becomes coherent in a broader framework. There is also something elegant about how imaginary numbers interact with real numbers. Together they form complex numbers, which can be added, subtracted, multiplied, and divided without contradiction. The system is closed and balanced. Every polynomial equation, no matter how complicated, has solutions within the complex numbers. This fact is known as the fundamental theorem of algebra. It means that the complex number system is complete in a way the real numbers alone are not. The imaginary unit fills in the gaps. It reminds us that absence of a solution may simply mean we are looking within too narrow a space. Visualize again the complex plane, a calm grid extending infinitely in all directions. Points scattered across it represent numbers with both magnitude and direction. Each number can also be described in terms of distance from the origin and angle of rotation. This connection between algebra and trigonometry allows exponential growth to blend with circular motion, as we saw in Euler's identity. The imaginary unit is the bridge. Without I, the deep unity between exponential functions and trigonometric waves would remain hidden. There is something quietly reassuring about this. A concept once considered fictitious becomes essential. A mathematical outsider becomes central. The imaginary unit encourages flexibility in thought. It shows that expanding definitions can lead to harmony rather than confusion. It also teaches humility. What seems impossible within one framework may become natural within another. As you let the idea of E settle in your mind, imagine the gentle rotation it represents. A quarter turn, another quarter turn, a smooth cycle returning to its starting point. Movement without chaos, extension without disorder. The imaginary unit is not a rebellion against logic, it is a refinement of it, and perhaps that is why understanding it, even slightly, feels quietly empowering. You begin to see numbers not just as positions on a line, but as points in a plane. Not just quantities, but transformations. What began as the square root of -1 becomes a doorway into a richer landscape. And in that expanded landscape, even the impossible finds its place. The heat equation begins with something familiar. Imagine placing a metal rod into a fire. One end becomes hot, while the other end remains cool. If you wait long enough, the heat begins to spread. The hotter region slowly transfers energy to the cooler region. Over time, the temperature evens out. This gentle spreading process can be described with a single mathematical relationship. Spoken in words, the heat equation says this: the rate at which temperature changes over time is equal to a constant number multiplied by the second derivative of temperature with respect to space. That may sound technical at first, so let us slow it down. The rate of change over time simply means how quickly the temperature is rising or falling at a particular point. If something is heating up rapidly, that rate is large. If it is barely changing, the rate is small. The second derivative with respect to space measures how curved the temperature distribution is along the rod. If one point is much hotter than the points around it, the curve is steep and bent. If temperatures are nearly uniform, the curve is almost flat. So the heat equation tells us something calm and intuitive. Temperature changes quickly in places where there is strong curvature, where there is imbalance. And it changes slowly where things are already smooth. In simpler terms, heat flows from regions of high concentration to regions of low concentration, smoothing out differences. The constant number in the equation is called the diffusion constant. It depends on the material. Metal conducts heat quickly, so its diffusion constant is larger. Wood conducts heat slowly, so its diffusion constant is smaller. But the structure of the equation remains the same. Take a moment to visualize a graph of temperature along a rod. At the beginning, perhaps the left side is very hot and the right side is cool. The graph slopes downward sharply. As time passes, that sharp slope softens, the peak lowers, the valley rises. The curve becomes smoother and flatter. The heat equation describes this gradual evening out with quiet precision. There is something deeply calming about this idea. No matter how sharp the initial difference, diffusion works steadily to reduce extremes. High concentrations disperse, low concentrations fill in. The process does not overshoot wildly. It does not oscillate dramatically. It simply smooths. Mathematically, this smoothing effect has an important property. If the temperature distribution starts out continuous, it remains continuous. In fact, it becomes even more regular over time. Sharp edges soften. Irregularities fade. Imagine placing a drop of ink into still water. At first, the ink is concentrated in one small region, but slowly, almost imperceptibly, it spreads outward. The color becomes lighter and more evenly distributed. The same principle governs heat. This equation does more than describe metal rods. It applies to many systems: the diffusion of particles in air, the spread of pollutants in water, even the movement of probability in certain random processes. It is a universal law of smoothing. The mathematical form of the heat equation is a partial differential equation. That means it involves derivatives with respect to more than one variable, usually time and space. But we do not need to focus on the technical language to appreciate its structure. At its heart, it says that change in time depends on curvature in space. If the temperature graph bends sharply upward at a point, meaning it is lower than its neighbors, heat flows inward and the temperature rises. If it bends sharply downward, meaning it is higher than its neighbors, heat flows outward and the temperature falls. The system constantly seeks equilibrium. Take a slow breath and imagine that graph flattening over time. Peaks lowering, valleys rising, differences dissolving. Eventually, if no new heat is added, the rod reaches a uniform temperature. The graph becomes a flat line. The rate of change becomes zero. The curvature becomes zero. The system rests. There is something philosophical in this behavior. Imbalance generates motion. Curvature creates change. But as balance approaches, motion slows. Extremes cannot sustain themselves indefinitely in a diffusive system. They spread their intensity into the surrounding environment. This principle appears beyond physics. In economics, wealth distributions can diffuse. In social networks, ideas spread from concentrated sources. In probability theory, uncertainty disperses. The equation itself does not judge. It does not rush. It simply encodes a pattern of gradual equalization. One of the remarkable features of the heat equation is that it has explicit solutions in many cases. For example, if the initial temperature distribution is a sharp spike at one point, the solution over time becomes a bell-shaped curve known as a Gaussian distribution. That bell curve widens as time increases. The peak lowers. The width expands. Total energy remains conserved, but it spreads more thinly across space. Again, smoothing without loss of total quantity. There is also something interesting about reversibility. Many equations in physics can be run backward in time, but the heat equation resists this. If you start from a smooth distribution and try to determine the exact sharp pattern that produced it, tiny uncertainties grow dramatically. Diffusion erases detail. It moves from structure to smoothness, from sharpness to calm. This directional flow gives the heat equation a subtle connection to the idea of time's arrow. Processes that diffuse tend to increase entropy, a measure of disorder. Systems naturally evolve toward uniformity, and yet uniformity in this context feels peaceful rather than chaotic. Imagine holding a warm cup of tea in a cool room. The warmth slowly radiates outward. The temperature difference diminishes. Eventually, the cup and the room share the same temperature. No drama, just gradual balance. The heat equation captures that inevitability. It reminds us that change often happens quietly, that differences tend to soften, that systems seek equilibrium, and as we reflect on its structure, we see that a simple relationship between rates of change and curvature can describe something as tangible as warmth spreading through metal. The symbols may appear formal, but the story they tell is gentle. Heat moves, curves flatten, extremes fade, and in that steady motion toward balance, there is something quietly reassuring. The wave equation begins not with stillness, but with motion. Imagine holding one end of a long rope. You flick your wrist gently upward. A ripple forms and travels along the rope, moving away from you. The rope itself does not travel across the room. Each small piece only moves up and down. And yet, the disturbance travels forward. This quiet transmission of motion is what we call a wave. The wave equation describes this behavior with remarkable simplicity. Spoken in words, it says, the second derivative of displacement with respect to time equals the wave speed squared multiplied by the second derivative of displacement with respect to space. Let us slow that down. The displacement is how far a point on the rope has moved from its resting position. The second derivative with respect to time measures acceleration, how quickly the motion itself is changing. The second derivative with respect to space measures curvature, how bent or stretched the rope is at a particular point. So the equation tells us something intuitive. The acceleration of a small piece of the rope depends on how curved the rope is at that point. If the rope is sharply curved upward, tension pulls it back down. If it is curved downward, tension pulls it upward. Curvature creates restoring force. And the constant in the equation, the wave speed squared, determines how quickly the ripple travels. A tighter rope produces a faster wave. A looser rope produces a slower one. Take a moment to visualize a smooth wave moving along the rope. A crest rises, then falls. A trough dips, then lifts. Each point oscillates gently up and down. But what is remarkable is that the shape of the wave can travel without changing form. If you create a smooth sine-shaped ripple, that shape can move steadily to the right at constant speed. The equation allows for such traveling wave solutions. In words, a simple solution looks like this. Displacement equals a function of space minus speed multiplied by time. That phrase, space minus speed multiplied by time, captures the idea of movement. As time increases, the position of the crest shifts forward. The wave equation is deeply connected to symmetry. It treats time and space in a balanced way. Both appear as second derivatives. Both describe curvature, one in time and one in space. This symmetry suggests something subtle. Motion and structure are intertwined. How something bends in space determines how it accelerates in time. Consider sound waves. When you speak softly, vibrations travel through the air. Tiny regions of air compress and expand. The wave equation describes these oscillations. Light itself can be described by a form of the wave equation. Electric and magnetic fields oscillate, propagating energy through empty space. Even water waves on a quiet lake follow similar mathematical patterns. The equation is not limited to ropes. It is a universal description of how disturbances move through a medium. Imagine standing at the edge of the ocean. Waves approach in steady rhythm. The surface rises and falls, but the water does not rush from the horizon to the shore in one mass. Energy travels, not matter. The wave equation captures this subtlety. There is something calming about periodic motion. A steady rhythm. A repeating pattern. Crest followed by trough. Rise followed by fall. The mathematics reflects this rhythm. Solutions often involve sine and cosine functions, which naturally oscillate between +1 and -1 in smooth cycles. If you freeze time, you see a curve in space. If you freeze space, you see a curve in time. The interplay between these two perspectives is elegant. Another remarkable feature of the wave equation is that it preserves shape. Unlike the heat equation, which smooths and diffuses, the wave equation maintains structure. A sharp pulse can travel without flattening out. This difference highlights two contrasting kinds of change. Diffusion erases detail. Waves carry detail forward. There is something philosophical in that contrast. Some processes smooth and equalize, others transmit and preserve. Imagine plucking a guitar string. The string vibrates. Standing waves form between fixed endpoints. Certain frequencies resonate more strongly than others. These natural frequencies are determined by the length of the string and the tension. They are solutions to the wave equation under specific boundary conditions. Each allowed vibration corresponds to a particular pattern. Nodes remain still. Antinodes oscillate fully. This structure explains harmony in music. Mathematical relationships govern which tones blend smoothly together. The wave equation therefore connects to sound, light, music, and motion. Take a slow breath and picture a single ripple traveling across calm water at sunset. The surface glows softly. The ripple moves outward in a perfect circle. The mathematics behind that motion is precise, yet the experience feels peaceful. In more advanced physics, the wave equation extends into multiple dimensions. Instead of one spatial direction, there may be two or three. The same principle applies. Acceleration in time equals wave speed squared times spatial curvature. The equation remains balanced. There is also a deeper connection to energy. Waves transport energy without permanently displacing matter. The rope returns to rest after the ripple passes. The water settles. The air grows still. Motion passes through, leaving equilibrium behind. This transient nature feels almost meditative. Disturbances arise, travel, and fade. The wave equation does not create the disturbance. It simply describes how it moves, and in that description, there is harmony. Curvature produces acceleration. Acceleration changes displacement. The cycle continues. Imagine the graph of a sine wave sliding steadily to the right. The peaks do not grow taller. The troughs do not deepen. The pattern endures. This persistence is encoded in the equation's symmetry. As you reflect on it, notice how different it feels from diffusion. Heat spreads and softens. Waves propagate and preserve. Both are forms of change. Both are governed by simple relationships between time and space. The wave equation reminds us that motion need not be chaotic. It can be rhythmic. predictable, structured, a ripple moving through still water, a tone resonating in quiet air, a beam of light crossing empty space, all guided by the same gentle principle. Acceleration follows curvature, and in that balanced relationship, motion becomes something almost serene. The Navier Stokes equations begin with something that is both familiar and endlessly mysterious: the motion of fluids, water flowing in a river, air moving around a wing, or oil slipping through a pipe. All these movements are governed by the same subtle principles. And yet, despite their commonness, the mathematics behind fluid motion remains one of the deepest unsolved mysteries in science. At first, consider a calm stream. Water moves in a smooth, almost meditative way. The surface glistens under sunlight, small ripples form and fade. If we were to measure the velocity of the water at different points along the stream, we would notice that each particle of water has its own speed and direction. Some move faster, some slower, some swirl gently in small eddies. The Navier Stokes equations describe this behavior mathematically. Spoken in words, one of the core relationships says that the rate of change of velocity at a point in space is equal to a combination of several factors: the pressure gradient at that point, the internal friction of the fluid, and any external forces acting on it, such as gravity. Each of these components interacts with the others in a quiet, continuous dance. The term for internal friction is called viscosity. It represents how the fluid resists motion between its layers. Honey, for example, has high viscosity. It flows slowly and resists deformation. Water has much lower viscosity. It flows smoothly and easily. The Navier Stokes equations include viscosity in a precise way, ensuring that the smooth, calming spread of motion is accounted for mathematically. Take a moment to imagine a flowing river again. At first glance, the motion appears random: ripples, small whirlpools, variations in speed. But underneath, there is structure. Fluid particles influence each other according to the balance of pressure and friction. The equations describe this structure, quietly predicting how motion develops over time. One remarkable feature of these equations is their universality. They apply to gases, liquids, and even plasmas under the right conditions. Whether you are observing clouds drifting across the sky or blood coursing through veins, the same underlying principles are at work. Yet, despite their elegance, the Navier Stokes equations are not fully solved in general. Mathematicians know the forms of the equations, but in 3 dimensions it remains unknown whether solutions always exist and remain smooth for all time. Small variations in initial conditions can lead to complex turbulence that seems almost chaotic. This sensitivity has earned the equations a reputation for mystery. Imagine swirling cream in a cup of coffee. At first, the cream forms smooth spirals. Then small eddies twist and fold, creating intricate patterns. The motion appears chaotic, yet it is still governed by the same principles encoded in the equations. What seems unpredictable is, in fact, structured beneath the surface. The equations themselves involve vectors representing velocity in 3 spatial directions and derivatives in both time and space. They encode how motion accelerates in response to pressure differences, viscous effects, and external forces. Each term contributes a subtle influence, gently shaping the evolution of the fluid's state. Philosophically, the Navier Stokes equations remind us of the delicate balance between order and complexity. Even a simple fluid system can produce turbulence, unpredictability, and intricate patterns. Yet underlying this apparent disorder is a continuous deterministic framework. Motion is never random in the absolute sense. It flows according to precise relationships. Visualize an ocean wave breaking gently on the shore. Each droplet follows a path influenced by its neighbors. Pressure gradients push some particles forward, viscous interactions slow others, and gravity pulls downward. The entire motion is encoded in a single system of equations, quietly capturing the interaction of countless elements. The equations also explain phenomena beyond our immediate perception. Airflow over a wing generates lift because layers of air accelerate differently above and below the surface. The rotation of hurricanes emerges from pressure and Coriolis effects, combined with viscosity. Blood flow in arteries responds to the pulsating pressure of the heart, following subtle Navier Stokes dynamics. There is a particular beauty in the way these equations link micro and macro behavior. Tiny local interactions between neighboring fluid particles accumulate into global patterns. Small curls and eddies combine to form waves, currents, and turbulence. This emergence from local rules to global motion is a quiet, pervasive theme in mathematics. Take another slow breath and picture a waterfall. The water accelerates as it falls, creating mist that dances in the air. Each droplet's motion is influenced by its own velocity, pressure from neighboring droplets, and air resistance. The pattern is complex, yet the principles governing it are constant. This is the essence of the Navier Stokes equations. Even the seemingly chaotic patterns of turbulence have structure. Mathematicians and physicists study energy cascades, where large vortices break into smaller ones, transferring motion across scales. This cascading process obeys the same equations that govern smooth laminar flow. What appears random is merely a higher level of organized complexity. From a reflective perspective, these equations encourage patience. Understanding a simple flow can take careful observation and subtle calculation. Predicting turbulence is extraordinarily difficult, yet the underlying rules are precise. There is a quiet lesson here. Even in systems that appear disorderly, order persists at a deeper level. The Navier Stokes equations also connect to computation. Modern simulations of fluid motion, from weather forecasting to aerodynamics, rely on approximations of these equations. Supercomputers solve millions of instances of the equations simultaneously, producing realistic representations of oceans, atmospheres, and engines. Yet even with vast computational power, some phenomena remain unpredictable. Tiny uncertainties in initial conditions can grow, leading to outcomes that seem almost random. This interplay between determinism and apparent chaos is one of the most intriguing aspects of fluid dynamics. Philosophically, the equations suggest that complexity is not the absence of rules, but the manifestation of rules at scale. Small interactions, repeated endlessly, create patterns that both inspire wonder and defy simple prediction. Imagine again a flowing river. Observe the ripples, the bends, the interactions with rocks and banks. The water appears alive, moving spontaneously. Yet beneath this appearance of spontaneity, the motion obeys exact mathematical laws. Each droplet influences its neighbors, just as each derivative term in the equations influences the whole system. The Navier Stokes equations remind us that life, like fluid motion, often balances between predictability and surprise. Steady flows coexist with turbulence. Calm regions coexist with spirals and eddies. And yet all are part of the same continuous framework. As you let this thought settle, imagine the flowing water of a river, the air around a swaying tree, the smoke curling from a candle flame. All these movements, at their core, follow the quiet guidance of the same principles. Each curve, swirl, and ripple is not random. It is a manifestation of precise, invisible relationships. The equations themselves may appear dense on a page with vectors and derivatives filling space, but their essence is simple. Motion follows pressure, friction, and force. Small differences accumulate, patterns emerge, and balance persists. And in that quiet balance, there is a sense of reassurance. The Navier Stokes equations capture the beauty of motion, the complexity of nature, and the subtle order underlying what seems chaotic. Watching water flow or air drift, one can glimpse, in a meditative way, the calm precision encoded in this remarkable mathematical system. The Scholes equation begins with a gentle recognition that uncertainty can be measured. In the world of finance, prices fluctuate, values rise and fall, and decisions must be made under the constant presence of risk. Yet mathematics allows us to describe this uncertainty in a structured, predictable way. The Scholes model is one of the most famous tools for doing just that. At first glance, the equation may seem like a tangle of symbols, but spoken in words it conveys a calm principle. The rate of change of an option's price with respect to time depends on the rate of change with respect to the underlying asset, the asset's volatility, and the risk-free interest rate. Each term interacts with the others, creating a balance that allows us to determine the fair price of certain financial contracts known as options. To slow this down, let us begin with the concept of an option. An option is a contract that gives the holder the right, but not the obligation, to buy or sell an asset at a specific price on or before a specific date. There are two main types: a call option, which allows purchase, and a put option, which allows sale. Prices of options fluctuate as the underlying asset's price changes, as time passes, and as uncertainty shifts. The Scholes equation models this fluctuation. One of the key insights is that we can use continuous time mathematics to represent how the option's value evolves. Let us consider the main components. First, the underlying asset's price. It is represented as a continuous variable that can move up or down in tiny increments, following a random yet statistically predictable pattern known as geometric Brownian motion. This motion is continuous, smooth in infinitesimal steps, yet over time it produces variability. Second, volatility. This represents how much the underlying asset's price tends to fluctuate. High volatility implies that prices can swing widely, while low volatility implies steadier movement. Volatility is squared in the equation, reflecting its effect on the curvature of the option's price relative to the underlying asset. Third, the risk-free interest rate. This is the return one would expect from an absolutely safe investment, like a government bond. It influences the option price gently, as the time value of money is incorporated into the calculation. Finally, the passage of time. As an option approaches its expiration, its value changes even if the underlying asset remains steady. Time decay is a subtle force that the Scholes equation accounts for continuously. Mathematically, the equation can be interpreted as describing diffusion, similar to heat flowing along a rod. The price of the option spreads, influenced by volatility, the underlying asset's motion, and the passage of time. The analogy to heat is not accidental. Both involve partial differential equations with second derivatives representing curvature, first derivatives representing drift, and a temporal term representing evolution. Consider the final boundary condition. At expiration, the option's value is known precisely. For a call option, it is the maximum of zero or the difference between the asset's price and the strike price. For a put option, it is the maximum of zero or the strike price minus the asset's price. This acts as a calm anchor in the model, a point where uncertainty resolves completely. To visualize the equation, imagine a smooth surface representing the option's value across time and asset price. Peaks correspond to high value, valleys correspond to low value. As time progresses, the surface evolves gently, guided by the curvature in asset price and the steady pull of time decay. The peaks shift, the slopes adjust, yet the surface remains continuous. An elegant feature of the Scholes model is its closed-form solution for European options. European options are those that can only be exercised at expiration. The solution uses functions from probability theory, specifically the cumulative normal distribution. In words, the price of a call option equals the current asset price multiplied by the probability that it will end above the strike price, minus the discounted strike price multiplied by the probability that it will be exercised. The cumulative normal distribution introduces a gentle smoothing effect. It captures the idea that uncertainty is not binary. The asset does not simply end above or below a threshold. Instead, outcomes are distributed in a continuous probabilistic way. The equation calculates expected value, quietly averaging across all possibilities. Volatility, again, plays a central role. It determines the width of the probability distribution. High volatility spreads the possible outcomes farther apart, increasing the option's value because the chance of favorable outcomes rises. Low volatility compresses the outcomes, decreasing the option's value. Time also interacts subtly with volatility. The longer until expiration, the greater the effect of volatility, because there is more opportunity for the asset price to move. As expiration approaches, the influence of volatility diminishes, while the time decay effect grows stronger. From a philosophical perspective, the Scholes equation reveals how structure can emerge from uncertainty. We begin with randomness, a world of fluctuating prices, yet by considering small incremental changes and combining them into a continuous model, we derive a formula that predicts fair value calmly and reliably. Imagine observing the stock market for a day. Prices fluctuate wildly, yet the equation distills this apparent chaos into a smooth landscape of value, incorporating uncertainty, time, and risk-free growth. It transforms unpredictability into structured expectation. The equation also shows the subtle connection between mathematics and reality. Probability, calculus, and continuous motion converge to produce something tangible, a number that guides financial decisions. It transforms abstract reasoning into practical insight, all while maintaining the elegance of the underlying principles. Take a moment to imagine a smooth curve representing the value of a call option. Over time, the curve shifts gently as the underlying asset price moves. Peaks rise or fall based on volatility. Slopes adjust according to interest rate and time. Every small adjustment reflects continuous interaction of forces, yet the overall evolution is serene, predictable, and bounded. The Black-Scholes equation also illustrates a more general lesson. In complex systems, uncertainty can be quantified. Processes that seem random on a small scale may follow patterns that are tractable and harmonious when viewed continuously. The equation captures that harmony. It reminds us that careful observation and structured reasoning allow us to navigate apparent chaos. The gentle progression of the option's value, guided by the equation, is both practical and meditative. In the end, the Black-Scholes model is more than finance. It is an example of mathematics' ability to describe motion, change, and uncertainty in a coherent and elegant way. The world of fluctuating prices, risk, and chance becomes a landscape of calm, continuous evolution. And as we reflect on it, we can imagine the quiet motion of probabilities, the gentle curvature of value, and the structured unfolding of uncertainty. What once seemed unpredictable becomes something gracefully mapped, a testament to the subtle power of mathematics to impose order on even the most dynamic systems. The concept of Shannon entropy begins with a question about uncertainty. How much information is contained in a message? How unpredictable is a sequence of events? How can we quantify the randomness of a system in a precise mathematical way? Claude Shannon, often called the father of information theory, gave us a framework to do just that. At first glance, entropy may seem like an abstract idea, but we can understand it with simple examples. Imagine flipping a fair coin. Each flip has two possible outcomes, heads or tails. Because the coin is fair, each outcome is equally likely. There is uncertainty before the flip. Each flip carries information. We do not know the result until it occurs. Shannon entropy allows us to measure the average amount of information per flip. In words, the formula for Shannon entropy says, take the negative sum of the probability of each possible outcome multiplied by the logarithm of that probability. If we have outcomes with probabilities P1, P2, P3, and so on, the entropy H equals negative P1 times log base 2 of P1 minus P2 times log base 2 of P2 of P2, minus P3 times log base 2 of P3, and so on, summing over all possibilities. Why the logarithm? The logarithm measures information in bits, the smallest units of information in binary systems. It also captures the idea that unlikely events carry more information. If something is almost certain, its occurrence is not surprising, and thus it carries little new information. If something is unlikely, observing it gives more information. Consider a simple example. A fair coin flip has two equally probable outcomes, each with probability 1/2. The entropy is negative 1/2 times log base 2 of 1/2, minus 1/2 times log base 2 of 1/2. The logarithm of 1/2 is negative 1, so each term becomes 1/2. Summed together, the total is 1 bit. This is intuitive. Each fair flip gives exactly 1 bit of information. Now imagine a bias coin where heads occurs with probability 3/4 and tails with probability 1/4. The entropy is calculated as negative 3/4 times log base 2 of 3/4 minus 1/4 times log base 2 of 1/4. The first term is roughly negative 3/4 times negative 0.414, or about 0.31. The second term is -1/4 times -2, which is 0.5. Summed together, the total entropy is approximately 0.81 bits. Notice the subtle principle here. Uncertainty decreases when outcomes are unevenly distributed. The biased coin is more predictable than the fair coin, so it carries slightly less information per flip. Shannon entropy quantifies this difference precisely. Entropy can be applied to more than coins. Consider letters in English text. Some letters, like E, occur frequently, while others, like Q, are rare. A text composed entirely of E's would be highly predictable and have low entropy. A text with letters evenly distributed would have higher entropy. In this way, Shannon entropy measures the richness and unpredictability of information. Imagine transmitting a message over a noisy channel. The presence of noise introduces uncertainty. Some bits may be flipped, changing the message. Shannon's insight was that entropy quantifies the minimum number of bits required to encode the information without loss. It defines a fundamental limit on data compression. Entropy also connects to probability distributions beyond simple discrete examples. Continuous distributions have differential entropy, measuring the average information per continuous observation. This extension allows us to analyze systems ranging from thermodynamics to communication networks. There is also a philosophical layer to Shannon entropy. It reminds us that information is inherently tied to uncertainty. Knowledge reduces entropy. Ignorance maintains it. Each observation, each measurement gently shifts the balance from uncertainty to clarity. Take a moment to visualize a sequence of coin flips. At first, the outcomes are unknown, scattered possibilities extending infinitely into the future. Each flip resolves one bit of uncertainty, a small act of ordering the unknown. Shannon entropy measures this ordering process. In communication systems, engineers use entropy to design efficient codes. Highly predictable messages can be compressed into shorter representations, while unpredictable messages require more bits. The principle is subtle. Information is not about content alone, but about unpredictability. Entropy also appears in natural systems. Biological sequences like DNA carry information in nucleotides. Shannon entropy allows us to measure diversity and redundancy. A genome with repeating sequences has lower entropy. A genome with varied sequences has lower entropy. A genome with varied sequences has higher entropy. Consider a random number generator. A truly random sequence has maximal entropy because each outcome is unpredictable. In contrast, a deterministic sequence repeating a simple pattern has low entropy. The measure guides our understanding of randomness, both practical and philosophical. Shannon's framework reveals that uncertainty is not a flaw, it is a property that can be quantified. By measuring entropy, we gain insight into the structure of information. Randomness becomes a landscape we can explore mathematically. Now imagine a series of messages arriving over time. Each message carries its own bits of uncertainty. The total entropy reflects the combined unpredictability. If messages are correlated, the total entropy is less than the sum of individual entropies. This subtle interaction captures redundancy, repetition, and structure in information. Entropy also informs error correction. By understanding the inherent unpredictability, we can design codes that protect against noise. Redundant bits are added strategically, ensuring that messages can be reconstructed even when some information is lost. From a reflective perspective, Shannon entropy is deeply meditative. It teaches us to observe systems quietly, noting which outcomes are likely and which are rare. It quantifies the gentle rhythm of uncertainty and the structure that emerges when probabilities interact. Take another slow breath and imagine a field of possibilities. Each point represents a potential outcome. Some points are crowded, likely, and familiar. Others are sparse, rare, and surprising. Shannon entropy measures the density of these possibilities. It tells us how much information is hidden in the uncertainty, waiting to be revealed. The concept also extends beyond mathematics. Life itself can be viewed through the lens of entropy. Choices, events, and observations reduce uncertainty incrementally. Each moment carries potential information. Each realization transforms the unknown into the known. Shannon Entropy, in this sense, is more than a formula. It is a quiet meditation on knowledge, randomness, and the flow of information. It connects probability, communication, and observation in a way that is precise, yet gently philosophical. As you reflect on it, imagine sequences of symbols, waves of probability, and unfolding events. Each step carries information. Each resolution reduces uncertainty. And through this lens, the world can be seen as a landscape of possibilities where entropy measures the richness, complexity, and subtle rhythm of the unknown. In Shannon Entropy, we find a bridge between mathematics and perception. We see how uncertainty can be quantified, how randomness can be measured, and how information flows steadily from the unknown into understanding. It is a reminder that even in uncertainty, there is structure, elegance, and quiet beauty. Bayes' theorem begins with a gentle idea that our knowledge can be updated as we observe the world. Life is full of uncertainty, and often we do not know the truth directly. But we can gather evidence, consider what we already believe, and refine our understanding. Bayes' theorem provides a quiet, precise framework for this process. At its core, Bayes' theorem is a relationship between probabilities. Spoken in words, it says, the probability of a hypothesis given observed evidence equals the probability of the evidence given the hypothesis multiplied by the prior probability of the hypothesis, all divided by the probability of the evidence. In simpler terms, our updated belief depends on how likely the evidence is under our assumption, adjusted by how strongly we believed in the assumption to begin with, normalized by how likely the evidence is overall. To understand this gently, imagine a scenario. Suppose there is a rare disease that affects 1 in 1,000 people. A test exists that detects the disease 99% of the time when a person has it, and it incorrectly signals positive for 1% of healthy people. If someone tests positive, how likely is it that they actually have the disease? Intuition often leads us astray here. The raw success rate of the test does not directly give the probability we want. Bayes' theorem corrects this by combining prior knowledge, the rarity of the disease, with the test results. Let us slow this down. Define the following. The prior probability is the initial belief, 1 in 1,000. The likelihood is the probability that the test shows positive if the person has the disease, 99%. The false positive rate is the probability that the test shows positive for someone without the disease, 1%. The denominator, the total probability of a positive test, accounts for both cases, true positives and false positives. The calculation proceeds quietly. Multiply the prior by the likelihood to get the probability of a true positive weighted by the rarity. Then compute the probability of a positive test overall by adding the contributions from true positives and false positives. Dividing these gives the posterior probability, the refined belief after observing the test result. Surprisingly, even with a highly accurate test, the posterior probability may be much lower than intuition suggests. If a rare disease occurs in only 1 in 1,000 people, a positive result might indicate only about a 9% chance of actually having the disease. This counterintuitive outcome reveals the subtlety of conditional reasoning. Bayes' theorem can be applied far beyond medical tests. It governs how we update beliefs in science, how artificial intelligence interprets data, and how humans make decisions under uncertainty. Consider weather forecasting. If the morning sky is cloudy, the probability of rain increases. But the update depends on prior climate data, historical frequency of rain on cloudy mornings, and the reliability of cloud observations. Bayes' theorem formalizes this quiet process of weighing evidence. Mathematically, Bayes' theorem also connects to probability distributions and continuous variables. For instance, in signal processing, one may estimate a signal in the presence of noise. The theorem provides a way to update the estimate as new measurements arrive, refining accuracy incrementally. There is a philosophical resonance here. The theorem embodies a dynamic view of knowledge. Belief is never static. Each observation subtly shifts understanding. Uncertainty is not eliminated instantly, but is reduced progressively, layer by layer, like light filtering through a mist. Take a moment to visualize this process. Imagine a cloud of possibilities. Each hypothesis occupies a region of space. Observations gradually sculpt the cloud, concentrating probability in some areas, thinning it in others. The shape changes continuously as evidence accumulates. Bayes' theorem dictates this transformation quietly and systematically. Even in everyday life, this process is at work. Suppose you hear footsteps in the hallway at night. Your initial assumption might be that it is a housemate. If you hear unusual sounds, you update your belief, considering other possibilities. Each observation adds information, refining the probabilities of different explanations. The theorem also has deep connections to machine learning. Bayesian methods allow computers to update models as new data arrives, handling uncertainty in predictions. This incremental learning mirrors human intuition, but in a rigorously mathematical way. Each new piece of information nudges the system toward more accurate predictions, maintaining consistency while incorporating flexibility. One subtlety worth noting is the choice of prior probability. The prior reflects what we believe before seeing the evidence. Sometimes this prior is subjective, reflecting experience or knowledge. Sometimes it is based on symmetry or fairness. The beauty of Bayes' theorem is that no matter the prior, evidence updates the belief logically. Over time, as more observations accumulate, the influence of the prior diminishes, and the posterior probability increasingly reflects reality. Imagine updating beliefs step by step. Each observation shifts the probability distribution gently. The process is continuous, methodical, and almost meditative. The cloud of uncertainty becomes gradually more focused. Peaks rise where evidence aligns, valleys deepen where it does not. Bayes' theorem also connects to broader philosophical ideas. It demonstrates that knowledge is provisional, always conditional on what we have observed. Absolute certainty is rare. Instead, understanding emerges as a balance between prior assumptions and empirical evidence. There is elegance in this humility. Consider another example: spam filters in email. A filter starts with a prior belief about words commonly associated with spam. Each incoming message is examined. Words like lottery or prize increase the likelihood of being spam, while familiar contacts reduce it. The filter continuously updates its estimate using Bayes' theorem, gently learning patterns without rigid assumptions. The theorem also scales beautifully. For multiple pieces of evidence, the updating process can be applied sequentially. Each new observation becomes a refinement, a gentle adjustment to the posterior, which then serves as the new prior for the next update. Over time, the system becomes increasingly calibrated, combining intuition and experience in a precise, mathematical manner. Reflect for a moment on how this mirrors human learning. Children observe, gather data, and adjust expectations. Scientists collect experiments, revise hypotheses, and refine models. Each step is small, incremental, and guided by the logical structure that Bayes' theorem formalizes. There is also a quiet beauty in the symmetry of the formula. The probability of hypothesis given evidence is proportional to the probability of evidence given hypothesis, weighted by the prior. Information flows both ways. Evidence informs belief, and belief guides interpretation of evidence. In essence, Bayes' theorem teaches patience and reflection. It encourages observing carefully, accounting for prior knowledge, and updating gently in response to new information. It provides a calm mathematical lens through which to view uncertainty, whether in medicine, science, finance, or daily life. Take a slow breath and visualize this landscape of probabilities. Each observation nudges the distribution, refining peaks, lowering valleys, concentrating likelihood where truth is supported. Uncertainty diminishes, not abruptly, but through steady, incremental adjustment. Bayes' theorem transforms the abstract notion of probability into a practical, philosophical, and meditative framework. It reveals that knowledge is dynamic, structured, and adaptable. What begins as uncertainty evolves into clarity through the quiet, systematic interplay of prior belief and evidence. In this gentle unfolding, there is both power and serenity. The world of the unknown becomes a landscape we can navigate logically, observing, updating, and gradually approaching understanding. Bayes' theorem embodies the quiet elegance of reason applied to uncertainty, turning the unpredictable into something thoughtfully comprehensible. The Fourier Transform begins with the quiet recognition that patterns often hide beneath apparent complexity. Consider a song playing softly in the background. Your ears hear a mixture of notes, harmonies, and rhythms. Each sound seems layered, interwoven with others. To the untrained ear, it is a single flowing experience. But mathematically, each complex signal can be decomposed into a sum of simple, pure oscillations. This is the insight that underlies the Fourier Transform. Spoken in words, the Fourier Transform is a mathematical operation that takes a function of time and represents it as a function of frequency. Essentially, it tells us how much of each pure tone is present in a complex signal. Every vibration, no matter how intricate, can be expressed as a combination of sine and cosine waves. Each wave has a frequency, amplitude, and phase, and together, they recreate the original signal perfectly. Let us slow this down. Imagine a simple sound, a pure note from a tuning fork. This note corresponds to a single sine wave. Its frequency is constant, its amplitude fixed. Now imagine a piano chord when multiple notes sound simultaneously. The waveform in time looks complicated, with peaks and valleys that seem unpredictable. Yet the Fourier Transform reveals that beneath the complexity, there are only a few distinct frequencies, each contributing its own sine wave. Mathematically, the transform involves integrating the original function multiplied by a complex exponential. Spoken in words, we are taking the signal, multiplying it by oscillations at different frequencies, and summing over time. The resulting value for each frequency indicates how strongly that frequency is present. A large result means the frequency is dominant. A small result means it is weak. Take a moment to visualize this. Imagine a waveform stretching across time, rising and falling. The Fourier Transform scans across each possible frequency, gently asking, how much of you is present here? Each frequency receives a weight, a contribution, quietly revealing the hidden structure of the signal. The beauty of the Fourier Transform is that it applies to signals of any kind. Sound, images, vibrations, electrical currents, all can be analyzed in this way. A complex waveform becomes a spectrum of frequencies, each represented by a peak in the frequency domain. Peaks tell us which oscillations dominate. Valleys show which are absent. Consider a gentle example: the human voice. A single spoken word contains fundamental frequencies and harmonics. The Fourier Transform separates these, allowing us to see which tones define the sound. Speech recognition systems, audio compression algorithms, and musical analysis all rely on this transformation. It converts the seemingly chaotic into orderly components. There is also a subtle philosophical lesson. Complex phenomena often appear random or dense, but they may have hidden regularity. The Fourier Transform reveals that underneath apparent chaos, there is order, rhythm, and structure. Even the most intricate signals can be understood as combinations of simple oscillations. Take another example: an image. A picture of a mountain at sunrise may look static, but mathematically it can be seen as a two-dimensional signal. Each row and column of pixels represents variation in brightness. Applying a two-dimensional Fourier Transform decomposes the image into spatial frequencies. High frequencies capture edges and fine details. Low frequencies capture gentle gradients and large shapes. The picture is reconstructed by summing these contributions. From a meditative perspective, this is a quiet reminder of the universe's hidden harmony. Waves, vibrations, and fluctuations are everywhere. Even seemingly irregular patterns, ocean waves, wind, heartbeats, can be understood as combinations of underlying oscillations. The Fourier Transform acts as a lens, gently exposing the structure beneath complexity. In electrical engineering, the Fourier Transform is fundamental. Alternating currents, radio waves, and digital signals are all analyzed in the frequency domain. Filtering out noise, isolating specific frequencies, and compressing data rely on this transformation. A signal that is noisy in time may become orderly in frequency. The operation provides clarity, efficiency, and understanding. Consider again music. A symphony is a rich, layered sound. The Fourier Transform allows composers and audio engineers to see each instrument's contribution. Even in a cacophony, there is quiet structure. Violins dominate certain ranges, flutes others, and percussion punctuates patterns. This is mathematics as both analytic tool and meditative exploration. The Fourier Transform also reveals deep connections in mathematics. It is closely related to harmonic analysis, differential equations, and even quantum mechanics. In quantum systems, wave functions can be represented in position space or momentum space. The Fourier Transform bridges the two, connecting complementary perspectives. One domain emphasizes location, the other emphasizes frequency. Yet both describe the same reality. Take a slow breath and imagine a complex signal as a hidden landscape. Peaks and valleys in time are like mountains and valleys. The Fourier Transform scans across the horizon, identifying the fundamental rhythms underlying the surface. The resulting frequency spectrum is a map of vibrations, showing what is strong, what is weak, and how each component interacts. Philosophically, this teaches patience. Understanding a system may require stepping back, viewing it in a different dimension. What appears overwhelming in one perspective becomes orderly and comprehensible in another. Complexity is often a projection of simple, repeating patterns. Noise, too, can be understood through the Fourier Transform. Random fluctuations are spread across frequencies. Signals embedded in the noise can be extracted, revealing order within apparent disorder. In this way, the transformation is a tool for both analysis and clarity. From a reflective point of view, the Fourier Transform invites us to notice patterns quietly. Life, like a signal, contains visible and invisible layers. The highs and lows, the accelerations and pauses, can be decomposed into fundamental rhythms. Observing these layers transforms perception from confusion to understanding. Consider a heartbeat. The signal of the pulse contains a primary frequency corresponding to the rate of the heart, but secondary harmonics reflect subtle vibrations of blood flow, the resilience of arteries, and the rhythm of breathing. Fourier analysis of a heartbeat reveals these layers, exposing hidden beauty and structure. The mathematical elegance of the Fourier Transform lies in its invertibility. After decomposition into frequencies, the original signal can be perfectly reconstructed by summing the contributions. Nothing is lost. Complexity is never destroyed, only transformed into a different, revealing perspective. Even in continuous natural processes, the Fourier Transform applies. Ocean waves, wind patterns, seismic tremors, and temperature fluctuations can all be analyzed in terms of their frequency content. Understanding these patterns allows prediction, control, and appreciation of underlying harmony. Imagine the gentle process of scanning a complex waveform, identifying its components, and reassembling them. Each frequency contributes a subtle vibration, a thread in the fabric of the signal. The operation is quiet, systematic, and profoundly insightful. Ultimately, the Fourier Transform teaches that beneath apparent complexity lies simplicity. Waves, vibrations, and fluctuations are the universe's building blocks. By decomposing and reconstructing signals, we see order where there seemed only chaos, rhythm where there seemed only randomness. Take a slow, deep breath and picture a landscape of sound, light, or movement. Peaks of intensity rise and fall. Waves overlap and intertwine. Each component is a simple oscillation. The Fourier Transform gently separates them, allowing us to observe the underlying structure, appreciate its elegance, and feel the quiet coherence of a world built from waves. In this process, there is both understanding and calm. Complexity yields to pattern, confusion yields to rhythm. The Fourier Transform is a bridge between observation and insight, between the tangled surface of experience and the underlying simplicity of the universe. The Schrodinger Equation begins with a quiet recognition that reality at its smallest scale behaves in ways that defy everyday intuition. In the microscopic world of atoms and subatomic particles, particles are not simply points moving along fixed paths. They exist as probabilities, as gentle waves of possibility, and the Schrodinger equation provides a precise description of this subtle, wave-like behavior. At its core, the equation tells us how the quantum state of a system evolves over time. Spoken in words, it says, the change in the wave function with respect to time is equal to the total energy operator known as the Hamiltonian, acting on the wave function, multiplied by the imaginary unit, and divided by Planck's constant, divided by 2 pi. Each term carries deep physical meaning, and together they describe how probabilities shift, how possibilities flow, and how the quantum world unfolds with precise, yet delicate, rules. To understand this gently, consider a single particle in a one-dimensional box. The particle cannot be in just one location with certainty. Instead, it exists as a wave function that describes the probability of finding it at each point along the box. Some regions are more likely, forming peaks in the wave function. Other regions are less likely, forming troughs. The Schrodinger equation dictates how these peaks and troughs evolve with time. The Hamiltonian represents the total energy of the system, kinetic energy associated with motion, and potential energy associated with forces acting on the particle. Kinetic energy is related to the curvature of the wave function in space. Greater curvature corresponds to higher momentum, gently illustrating the trade-off between localization in space and motion. Potential energy depends on the environment, walls of the box, electric fields, or gravitational gradients. Together, these energies shape the evolution of the wave function. Take a moment to visualize the wave function as a gentle, undulating surface extending along the spatial dimension. Peaks rise where the particle is likely to be observed. Valleys dip where the particle is less likely to appear. As time progresses, the surface may oscillate, spread, or interfere with itself. The Schrodinger equation governs this evolution quietly and systematically, ensuring that the total probability remains constant. One of the most fascinating aspects is the role of the imaginary unit. In quantum mechanics, the wave function is complex, having both real and imaginary parts. This allows interference, oscillation, and the richer structure than simple probabilities alone. The interplay of real and imaginary components gives rise to phenomena such as tunneling, superposition, and resonance. Consider a particle encountering a potential barrier. Classical intuition suggests that if the particle's energy is less than the barrier, it cannot pass. Yet, the Schrodinger equation predicts a non-zero probability that the particle can tunnel through the barrier, appearing on the other side. This gentle violation of classical expectation is fully described by the wave function and its evolution. Another profound concept is superposition. The Schrodinger equation allows the wave function to be a combination of multiple possible states simultaneously. A particle can be in a mixture of positions or energies, with each contributing to the overall probability distribution. Only when we measure does the system collapse into a specific outcome. The process is subtle and continuous, governed by the equation in a way that preserves the underlying coherence of possibilities. Take another example, the hydrogen atom. The electron does not orbit the nucleus like a tiny planet. Instead, its wave function forms standing waves around the nucleus with discrete energy levels. These solutions to the Schrodinger equation explain the spectral lines observed in atomic emission and absorption. Each energy level corresponds to a specific pattern in the wave function, a delicate balance of kinetic and potential energies. The equation is also linear, which means that if you have two solutions, their sum is also a solution. This property allows interference effects, where waves combine constructively or destructively, producing patterns that are rich, intricate, and sometimes surprising. These interference effects are observed in the double-slit experiment, where electrons form a pattern of bands even when sent one at a time, revealing their wave-like nature. The Schrodinger equation further connects to probabilities and measurements. The square of the magnitude of the wave function at a given point gives the probability density of observing the particle there. This is a quiet, subtle rule. The equation governs evolution, while measurement extracts information probabilistically. The two are intertwined, forming the philosophical heart of quantum mechanics. Imagine a gentle wave spreading along space. Each oscillation represents a possibility, a path the particle might follow. The wave evolves predictably under the Schrodinger equation, yet its interpretation requires a shift from classical certainty to probabilistic understanding. Peaks and troughs carry meaning, guiding expectations without dictating certainty. Time-independent solutions, for instance, describe stationary states. The wave function does not change shape over time. Its probability distribution is constant. Yet even stationary states contain phase information, oscillating in a complex plane, encoding subtleties invisible in classical terms. These solutions form the foundation for understanding atoms, molecules, and quantum wells. From a reflective perspective, the Schrodinger equation illustrates the elegance of structure underlying apparent randomness. Quantum phenomena often appear mysterious, even paradoxical, yet they follow exact rules. The evolution of possibilities is continuous, predictable, and governed by precise mathematics, even if outcomes of individual measurements remain probabilistic. The equation also extends naturally to multiple particles, higher dimensions, and interacting systems. In these cases, the wave function exists in a high-dimensional configuration space, capturing correlations and entanglements that defy classical intuition. Yet the principle remains the same. The Hamiltonian dictates the gentle evolution of possibilities across time. Take a slow breath and visualize the probability cloud of an electron in an atom. The cloud oscillates, spreads, and shifts in response to energy and potential. Each observation samples from this cloud, revealing one outcome, yet the underlying wave function continues evolving undisturbed. The Schrodinger equation ensures that every possibility is accounted for, every probability preserved. Even phenomena that seem fantastical, such as quantum tunneling in semiconductors or superconducting behavior, are governed by this same equation. The patterns of interference, resonance, and oscillation underpin technologies we use daily: lasers, transistors, MRI machines, and quantum computers. Mathematics becomes both predictive and meditative, revealing hidden structure in the microscopic world. Philosophically, the equation encourages humility and reflection. Reality at small scales is neither deterministic nor chaotic in a classical sense. It is structured, probabilistic, and elegant. The Schrodinger equation encapsulates this duality. It provides precise rules for the evolution of possibilities, while leaving room for uncertainty and measurement. Imagine again the gentle undulations of a wave function. Peaks rise and fall. Probabilities oscillate. Each point contains potential. Each measurement reveals one aspect, but the total structure persists. The equation is both a map and a meditation, showing us the hidden rhythm of the quantum world, encouraging us to see the universe as a continuous interplay of possibilities. In essence, the Schrodinger equation is more than mathematics. It is a lens into the subtle architecture of reality. It bridges waves and particles, certainty and uncertainty, mathematics and philosophy. Every undulation of the wave function whispers of hidden order, delicate balance, and the quiet logic underlying the unpredictable. As you reflect on it, imagine a single electron moving in its probability cloud, evolving under the gentle guidance of the Hamiltonian. It is neither here nor there, yet everywhere it can possibly be. The peaks and troughs of its wave function dance continuously, tracing a path of structured possibility. And through this lens, the microscopic world becomes a landscape of rhythm, order, and quiet elegance, revealed gently by the Schrodinger equation. The Maxwell equations begin with a quiet realization: electricity and magnetism, though seemingly separate forces, are deeply intertwined, flowing together in a harmonious dance that shapes the behavior of the universe. James Clerk Maxwell discovered that these forces are not isolated phenomena, but parts of a unified system, and he captured their essence in 4 elegant equations. These equations describe how electric fields and magnetic fields are generated, how they interact, and how they propagate through space as waves of light. At first glance, the Maxwell equations may appear abstract and filled with symbols, but spoken in words, each tells a calm, precise story. The first equation expresses that electric charges create electric fields. A positive charge radiates a field outward, a negative charge inward. The second equation states that there are no magnetic monopoles. Magnetic field lines always form closed loops, never beginning or ending at a single point. The third equation shows that changing magnetic fields induce electric fields, and the fourth states that moving electric fields create magnetic fields. Together, these equations form a quiet, interdependent system, describing the ebb and flow of electromagnetic phenomena. To understand this gently, imagine a simple magnet. Its magnetic field forms invisible lines looping from north to south poles. The lines exist even without motion, gently shaping the space around the magnet. Now imagine a nearby conductive wire. If the magnetic field changes, perhaps by moving the magnet, an electric field emerges in the wire, nudging electrons along a path. This is electromagnetic induction, one of the fundamental consequences of Maxwell's insight. Take a slow moment to visualize these interactions. Electric fields radiate from charges, like calm ripples in water. Magnetic fields circulate in loops, quiet yet persistent. As one changes, it gently gives rise to the other. The Maxwell equations describe this balance systematically, showing how local changes propagate through space. One remarkable implication is the existence of electromagnetic waves. When electric and magnetic fields oscillate together, they propagate through space at a constant speed. This speed, determined by the permittivity and permeability of free space, is precisely the speed of light. Thus, light itself is a manifestation of coupled electric and magnetic fields, an elegant ripple of energy traveling through the vacuum. Consider a radio wave gently drifting across a landscape. The oscillating electric field points in one direction, while the magnetic field oscillates perpendicular to it, and both are perpendicular to the direction of propagation. The fields sustain each other. A changing electric field generates a magnetic field, which in turn regenerates the electric field. This self-propagating dance continues quietly through space, carrying energy and information. From a reflective perspective, the Maxwell equations reveal the interconnectedness of nature. Electricity, magnetism, and light are not separate forces, but aspects of a single, coherent, electromagnetic reality. What seems complex and chaotic on the surface, static shocks, lightning, the glow of a bulb is underpinned by a simple, elegant framework. Let us consider the equations in sequence, in words to grasp their meaning more fully. The first, Gauss's law for electricity, states that the total electric flux out of a closed surface equals the total charge enclosed, divided by a constant called the electric constant. This relates charges to the fields they create, showing how localized sources influence space. The second, Gauss's law for magnetism, says that the total magnetic flux through a closed surface is zero. Magnetic field lines never start or stop. They always form continuous loops. This principle emphasizes symmetry and balance in the electromagnetic world, a quiet reminder of the completeness of natural laws. The third, Faraday's law of induction, states that the electromotive force induced around a closed loop equals the negative rate of change of the magnetic flux through the loop. A changing magnetic environment produces an electric response, a subtle interplay that underlies motors, generators, and transformers. The fourth, Ampere's law with Maxwell's addition, says that the circulation of the magnetic field around a closed path equals the current passing through, plus the rate of change of the electric flux. This final term, the displacement current, was Maxwell's key insight, allowing the prediction of electromagnetic waves. Without it, the equations would be incomplete, unable to describe light and radio waves. Imagine the gentle propagation of a wave in space. The electric field oscillates in one direction, the magnetic field oscillates perpendicular, and the wave travels forward, invisible yet powerful. This wave carries energy, momentum, and information, obeying the Maxwell equations without deviation. It is a calm, continuous manifestation of the interplay between electric and magnetic phenomena. The equations also connect deeply to modern technology. Wireless communication, electrical power transmission, lasers, and even the internet rely fundamentally on Maxwell's insight. signals travel as electromagnetic waves, guided by antennas and cables, following the same laws that govern light, radio, and microwaves. Mathematics predicts, controls, and explains these behaviors with serene precision. Consider reflection, refraction, and diffraction. When waves encounter boundaries, the Maxwell equations determine how they bend, scatter, or continue. Glass, water, and air guide light based on permittivity and permeability. Even subtle variations in materials, like lenses or fiber optic cables, are explained entirely through the framework of these four equations. Philosophically, the Maxwell equations demonstrate the beauty of unification. Forces once thought distinct, electricity and magnetism, merge into a single elegant structure. Patterns emerge from interactions. Waves propagate across empty space. Energy flows continuously, guided by simple principles. Nature's complexity arises not from arbitrary chaos, but from structured, lawful relationships. Take a moment to imagine the universe filled with invisible electromagnetic waves. Light from distant stars traverses interstellar space, gently bending around objects carrying energy, heat, and information. Radio waves whisper across continents. Microwaves heat food. The Maxwell equations describe all of this in a unified, serene mathematical framework. Even phenomena that seem mysterious, such as lightning or auroras, are manifestations of these principles. Electric fields build in clouds, discharge in sparks, creating moving charges and oscillating fields. The resulting light, the movement of charged particles, and the subtle magnetic interactions are all captured by the same equations. Mathematically, the four equations are coupled partial differential equations. They involve divergences and curls, relating fields to their sources and to each other. Yet their meaning can be felt intuitively. Charges create fields. Fields generate each other. Waves propagate, energy flows. The complexity of symbols mirrors the complexity of the universe, but the underlying structure remains calm and consistent. From a meditative perspective, one can imagine walking through a space filled with invisible electric and magnetic fields. They oscillate gently, interact subtly, and propagate quietly through the void. Their existence is continuous, orderly, and omnipresent, shaping the behavior of matter and light. The Maxwell equations also provide insight into the universality of physics. Light, radio waves, microwaves, and X-rays all obey the same principles. The speed of electromagnetic waves is constant in a vacuum, independent of frequency or wavelength, revealing the fundamental structure of space itself. This constancy became a cornerstone for the theory of relativity, showing that even time and space are intertwined with the behavior of fields. Take another gentle visualization: a beam of light crossing a quiet room. Electric and magnetic fields oscillate, perpendicular to each other and to the direction of travel. The beam carries energy silently, reliably, and predictably. Its behavior can be fully described by Maxwell's framework, revealing a hidden order behind every photon, every oscillation, every ripple in the electromagnetic continuum. Ultimately, the Maxwell equations teach us to observe nature in terms of relationships and interactions. No field exists in isolation. Electric and magnetic phenomena are inseparable. Waves propagate through space by the quiet interplay of fields, obeying exact mathematical rules that reveal both the simplicity and elegance of the underlying universe. As you reflect, imagine this invisible dance of fields surrounding you. Electric lines radiate gently from charges. Magnetic loops curl quietly in space. Waves propagate, carrying energy and information. The Maxwell equations are the calm, precise language describing these phenomena, offering a serene understanding of forces that, though unseen, shape our daily experience, technology, and the cosmos itself. The Cantor Diagonal argument begins with a quiet, unsettling insight. Infinity is not a single concept. There are different sizes of infinity, some larger than others, and some infinities that cannot be listed, counted, or captured completely. George Cantor, a mathematician in the late 19th century, revealed this subtle hierarchy, showing that even within the boundless, there is structure, surprise, and profound beauty. At first glance, the notion of comparing infinities may seem paradoxical. After all, Infinity seems infinite. How could one infinity be larger than another? Yet spoken in words, Cantor's argument shows a calm, methodical way to see that some sets, like the set of real numbers between 0 and 1, are uncountable, larger than the set of natural numbers, which are countably infinite. To understand this gently, imagine trying to list all real numbers between 0 and 1. You might start by writing 0.1, 0.14, 0.141, and so on. Perhaps you try to list them as decimals, one after another. The natural numbers, 1, 2, 3, and so forth, can enumerate the list, first, second, third, and so on. But Cantor's diagonal argument shows that no matter how carefully you attempt this listing, there will always be numbers left out, numbers that elude capture. The method is simple and elegant. Suppose we have a list of numbers between 0 and 1, written as infinite decimal expansions. Each number corresponds to a row in the list. We then construct a new number by taking the first digit of the first row, the second digit of the second row, the third digit of the third row, and so on, forming a diagonal. Then, we change each of these digits slightly, for example, adding 1 modulo 10, skipping 9 to avoid ambiguity. The resulting number differs from every number in the original list in at least one decimal place. Take a moment to visualize this. Imagine a grid of infinite decimal numbers, each row representing a number in the list. The diagonal runs gently from the top left to the bottom right. As we adjust each digit along this diagonal, a new number emerges, carefully crafted, quiet yet impossible to have been included in the original enumeration. No matter how complete the list seems, the diagonal process guarantees something missing. This construction demonstrates that the set of real numbers is uncountable. It cannot be matched one-to-one with the natural numbers. There is a larger infinity here, a richness that transcends the simpler infinity of counting numbers. The process is both unsettling and calming. Unsettling because it defies intuition, calming because it follows a logical, gentle method. Consider the philosophical implications. Countable infinity, like the natural numbers, integers, or rational numbers, can be arranged sequentially. Each element can be assigned a position in a list. Uncountable infinity, by contrast, contains elements that elude such ordering. The continuum of real numbers is dense, seamless, and larger than the discrete sets we might first imagine. Cantor's argument allows us to see the gradations within the infinite, a quiet exploration of the boundless. The diagonal argument also applies to functions and sets beyond numbers. For example, the set of all infinite sequences of zeros and ones is uncountable. Each sequence corresponds to a possible path through a conceptual space of possibilities. Applying the diagonal method constructs a sequence not in any proposed enumeration, revealing that the space of infinite sequences exceeds the size of the natural numbers. Imagine walking along the diagonal of an infinite grid of sequences. Each step reveals a new possibility. By altering each entry along this path, you generate a new sequence, guaranteed not to match any sequence in the list. It is a gentle construction, systematic, revealing a hidden hierarchy of infinities that is both logical and profound. Cantor's insight also bridges mathematics and philosophy. The concept of uncountable infinity challenges our perception of completeness. It reminds us that even infinite collections may have gaps, that the apparent vastness of one set may be dwarfed by another. It encourages reflection on the nature of abstraction, order, and possibility. Consider the continuum of points on a line segment. Each point corresponds to a real number. Even though the segment appears finite, its internal structure contains uncountably many points, a subtle richness hidden within the simplicity of the line. Cantor's diagonal argument gently reveals this structure, showing that infinity is layered, nuanced, and full of surprises. The argument also connects to logic and computability. Some numbers, such as certain real numbers, cannot be computed by any algorithm. They exist in principle as points on the continuum, but no finite procedure can enumerate them. The diagonalization method ensures their existence beyond any systematic listing, illustrating limits of computation and the power of abstract reasoning. Take a slow breath and imagine the infinite grid once more. Rows extend without end, columns stretch infinitely. Along the diagonal, each digit is nudged, transformed, and combined into a new number. This number, quiet and inevitable, escapes the confines of any enumeration. The process is meditative, showing how infinity contains hidden depth, subtle structure, and eternal surprise. Cantor also introduced the notion of cardinality, a measure of the size of sets. The cardinality of the natural numbers is denoted aleph null, a countable infinity. The cardinality of the real numbers, sometimes called the continuum, is strictly larger. The diagonal argument provides a simple yet profound proof of this distinction, showing that some infinities are fundamentally beyond the reach of counting. Consider the interplay between the countable and uncountable. Rational numbers, though dense on the number line, are countable. Real numbers include both rationals and irrationals. By diagonalization, irrationals alone form an uncountable set. The continuum is richer than any discrete enumeration, a quiet yet inexhaustible landscape of numbers. From a reflective perspective, Cantor's method encourages curiosity and patience. The diagonal argument is constructive yet gentle. It does not overwhelm. It gradually reveals the limitations of enumeration and the subtlety of the infinite. Infinity is not a monolith. It is a layered, structured, and profoundly intricate concept. Imagine exploring the continuum with the diagonal method as a compass. Each step identifies a number not yet encountered, a new point in the infinite landscape. The process continues indefinitely, revealing the vastness beyond any finite or countable list. It is both humbling and meditative, emphasizing that mathematical infinity is rich, subtle, and full of hidden beauty. Cantor's work also has implications for logic and set theory. Diagonalization underlies proofs of undecidability, incompleteness, and limits of formal systems. By constructing objects that escape systematic listing, mathematicians gain insight into the boundaries of knowledge, the structure of abstraction, and the hierarchy of infinite sets. Take another slow moment to visualize the grid, the diagonal, and the new number emerging. Each step is deliberate, each adjustment meaningful. The number constructed exists beyond the original list, quietly demonstrating the uncountable nature of the continuum. The simplicity of the method belies its philosophical depth, showing the power of reasoning applied to the infinite. In essence, the Cantor diagonal argument is a meditation on infinity. It teaches us to see beyond the obvious, to recognize that even boundless collections have structure, and to appreciate the delicate hierarchy within the infinite. By following the diagonal, we uncover hidden truths, explore the subtle landscape of real numbers, and glimpse the profound order underlying the concept of infinity itself. As you reflect, imagine the infinite grid stretching endlessly, the diagonal guiding your view, and the new number emerging quietly, inevitable, and uncountable. The process is logical, calm, and meditative, a journey into the boundless, revealing the hierarchy of infinity, the depth of mathematics, and the gentle elegance of Cantor's insight. The Fermat Mystery begins with a quiet whisper from history, a small note scribbled in the margin of a book, hinting at a truth that would remain elusive for centuries. Pierre de Fermat, the 17th century mathematician, wrote that he had discovered a marvelous proof of what is now known as Fermat's last theorem, but that the margin was too small to contain it. This simple claim, brief and enigmatic, opened a world of intellectual intrigue, challenge, and wonder that spanned generations. The theorem itself is straightforward to state, yet profoundly difficult to prove. Spoken in words, it says, there are no three positive whole numbers, no integers a, b, and c, that satisfy the equation a raised to the power of n plus b raised to the power of n equals c raised to the power of n for any whole number n greater than 2. For n equal to 2, we recognize the familiar Pythagorean theorem. Three numbers like 3, 4, and 5 satisfy 3 squared plus 4 squared equals 5 squared. But once we move beyond squares to cubes, fourth powers, and higher, Fermat claimed that no solutions exist. Take a moment to visualize this. Imagine the vast landscape of numbers stretching infinitely in all directions. Pythagorean triples form a gentle, recognizable pattern on this landscape. that when you attempt to find triples that satisfy the equation with powers greater than 2, the terrain becomes barren, empty of solutions. The theorem asserts that beyond squares, this simple harmony vanishes. For centuries, mathematicians tested Fermat's claim. They tried cubes, fourth powers, fifth powers, and higher. They confirmed the absence of solutions for small numbers, yet no general proof could be found. Each attempt was a meditation in patience, checking, verifying, calculating, and contemplating the subtle structure of numbers. The difficulty of the Fermat mystery lies in its deceptively simple statement. Unlike complex formulas filled with symbols, the theorem is understandable to anyone with basic arithmetic, yet its proof required tools that would not exist for hundreds of years: advanced algebraic geometry, modular forms, and elliptic curves. This juxtaposition of simplicity and depth is part of the quiet beauty of the problem. Imagine the search for a proof as a slow, contemplative journey. Mathematicians explored patterns in numbers, attempting clever factorizations, modular arithmetic, and infinite descent methods. Fermat himself used infinite descent for special cases, a method of assuming a solution exists, then showing a smaller solution must also exist, leading to a contradiction. Each step was careful, deliberate, and deeply reflective. One of the key insights came centuries later with the study of elliptic curves. These are smooth, continuous curves defined by cubic equations, often of the form y squared equals x cubed plus x plus b. Elliptic curves have rich internal structure, symmetry, and hidden relationships. Mathematicians realized that if a counterexample to Fermat's last theorem existed, it could be connected to a special type of elliptic curve. This connection, subtle and profound, became a bridge between number theory and geometry. Take a slow breath and imagine these curves, undulating gently for a coordinate plane. Each curve carries information about possible solutions. By analyzing their structure, mathematicians could infer properties that transcend simple numbers. The Fermat mystery began to transform from an arithmetic puzzle into a journey through abstract landscapes of mathematical beauty. The breakthrough came in the 20th century, when Andrew Wiles, a British mathematician, devoted years of quiet, concentrated effort to the problem. Using modular forms, which are highly symmetric functions with intricate patterns, and the Taniyama-Shimura conjecture, Wiles established a deep connection between these forms and elliptic curves. This bridge allowed him to prove that the kind of elliptic curve that would correspond to a counterexample to Fermat's last theorem could not exist. Imagine Wiles's thought process as a meditation on structure. Each lemma, each theorem, each connection was a step along a carefully mapped path. The problem that had resisted generations was approached not by brute force but by understanding the underlying architecture of mathematics. Patterns emerged, relationships crystallized, and the impossibility of solutions for powers greater than 2 became inevitable. Reflect on the philosophical aspect of this journey. A simple claim in a tiny margin inspired centuries of reflection, discovery, and creativity. It reminds us that the elegance of mathematics often hides in plain sight, waiting for persistent observation and deep insight. Fermat's statement was brief, yet it carried the weight of centuries of exploration, teaching patience, curiosity, and humility. Take another moment to visualize the infinite landscape of numbers once more. Squares create gentle hills and valleys where solutions exist. Cubes and higher powers leave empty plains. The vast emptiness is filled with subtle structure, discernible only with sophisticated tools, abstract thought, and quiet meditation on the properties of numbers. Even the process of attempting solutions is instructive. Infinite descent, modular arithmetic, factorization, and elliptic curves all reflect different perspectives on the same terrain. Each method uncovers new layers, new relationships, and new insights into the nature of numbers. The Fermat mystery becomes not just a theorem to prove, but a lens through which to understand the coherence and subtlety of mathematics itself. Andrew Wiles' proof, completed in 1994, closed the chapter on the Fermat mystery but opened new vistas. It demonstrated that centuries-old problems could be approached with modern, abstract tools. It highlighted the power of persistence, focus, and imaginative thinking. and it confirmed Fermat's claim. For powers greater than 2, no 3 positive whole numbers satisfy the equation. From a reflective perspective, the Fermat Mystery embodies the interplay between simplicity and depth, intuition and abstraction, curiosity and rigor. A statement understandable by a schoolchild required centuries of cumulative intellectual effort to resolve. It teaches that even the simplest questions can contain layers of complexity and profound beauty, quietly awaiting discovery. Imagine holding a number in your mind, thinking of all the others that might pair with it to satisfy the equation. Each attempt, each failure, each insight is a step along a subtle path, revealing the contours of possibility and impossibility. The Fermat Mystery is not only a testament to mathematics, but to patience, creativity, and the quiet wonder of exploring the infinite landscape of numbers. Even today, the Fermat Mystery inspires mathematicians, students, and enthusiasts alike. It reminds us that curiosity can endure across generations, that insight can emerge from the most minimal hints, and that the universe of mathematics is full of hidden connections, waiting for quiet attention and thoughtful exploration. In essence, the Fermat Mystery is a meditation on numbers, history, and human ingenuity. From a scribbled note in a margin to a monumental proof centuries later, it demonstrates that mathematics is not only a tool for calculation, but also a reflective, intellectual journey. It is a reminder that elegance, persistence, and deep thought can unlock secrets hidden quietly within the most familiar symbols. As you reflect, imagine the infinite landscape of integers stretching endlessly, the elusive solutions that cannot exist, and the gentle satisfaction of understanding their impossibility. The Fermat Mystery invites patience, observation, and a quiet appreciation for the depth, subtlety, and enduring beauty of mathematics. The Chaos Logistics segment begins with a quiet recognition. Simple rules can produce behavior so complex, unpredictable, and intricate that it appears chaotic. This is the essence of the logistic map, a mathematical model that demonstrates how deterministic systems governed by precise rules can generate surprising and beautiful complexity. It is a gentle journey into the boundary between order and chaos, a reflection on how the simplest formulas can conceal infinite subtlety. At its heart, the logistic map models population growth. Imagine a population of rabbits in a field. Each generation produces offspring constrained by resources, predation, and environmental limits. Let X represent the population as a fraction of the maximum sustainable size, and let R be the growth rate. Spoken in words, the logistic map says, the next generation's population equals the current population multiplied by 1 minus the current population multiplied by the growth rate. Symbolically, this is often written as x sub n plus 1 equals r times x sub n times 1 minus x sub n, but spoken aloud, it is a simple rhythmic rule. Take a slow moment to visualize this. Start with a small population fraction. Multiply it by the growth rate, then reduce it proportionally by the factor of 1 minus the current population. The resulting number is the next generation. Initially, the population may settle to a steady state, gently oscillating around a stable value. The system appears calm, predictable, meditative even, as if nature itself is whispering its quiet order. Yet as the growth rate increases, the behavior changes. At slightly higher values of R, the population begins to oscillate between 2 values. Increase R further, and the system oscillates between 4 values, then 8, then 16. This phenomenon is called period doubling, a slow and systematic transition from stability to chaos. The pattern is mesmerizing, as simple multiplication and subtraction produce a cascade of intricate behavior. Imagine following each generation, observing the fraction rise and fall. At first, the rhythm is gentle, a calm back and forth. But as the parameter R grows, the oscillations split and multiply. Peaks and troughs emerge, branch, and form a complex pattern, revealing the subtle sensitivity of the system to initial conditions. Each tiny change in the starting population leads to significantly different trajectories, a hallmark of chaos. At a certain threshold, the logistic map becomes fully chaotic. The population never settles. Values jump seemingly at random yet entirely determined by the underlying rule. There is no repetition, no simple pattern, but the behavior is not truly random. It is deterministic chaos arising from simple arithmetic, yet producing a landscape of infinite complexity. Take a moment to reflect on this delicate interplay. Chaos in this context is not disorder but an intricate, structured unpredictability. Even though exact predictions become impossible without infinite precision, the system obeys a precise rule. It is a dance of order and unpredictability, revealing the hidden depth within simple mathematical expressions. The logistic map also demonstrates fractal structure. When we plot successive population values against the growth rate, a bifurcation diagram emerges. Branches split repeatedly, forming self-similar patterns. Zooming in reveals smaller copies of the same structure like a forest of infinite branching trees. Each branch corresponds to a stable or periodic population cycle, and between the branches lie chaotic regimes. The diagram is a quiet visual meditation on complexity, arising from simplicity. Consider the philosophical implications. Systems governed by deterministic rules can exhibit behavior that seems random or unpredictable. Weather patterns, ecosystems, and even economies can behave in ways that are highly sensitive to initial conditions, echoing the logistic map's message. Tiny differences in starting values amplify over time, producing outcomes that are both beautiful and unpredictable. The logistic map also connects to the concept of the Lyapunov exponent, a measure of sensitivity to initial conditions. Positive exponents indicate chaos. Two initially close populations diverge exponentially over generations. Negative or zero exponents indicate stability. This gentle quantification provides insight into when simple systems become unpredictable, highlighting the delicate balance between order and chaos. Imagine again the population fraction evolving over time. With a low growth rate, the line gently settles, oscillating calmly. With higher growth rates, oscillations split and multiply. With the highest growth rates, the trajectory jumps erratically, tracing a path that is deterministic yet seemingly random. Each initial condition generates its own unique sequence, a quiet reminder of the subtlety of nature's laws. From a reflective perspective, the logistic map embodies patience and observation. By following generations carefully, one observes transitions from stability to periodicity to chaos. Patterns emerge slowly, revealing the structure beneath apparent unpredictability. Each step encourages awareness of sensitivity, interdependence, and the hidden depth in simple systems. The logistic map has applications beyond biology. It models chemical reactions, population dynamics, and even financial systems. In each case, the rule is simple, yet the outcomes are rich, complex, and sometimes counterintuitive. Small differences in input produce large variations in output, reminding us that complexity often lies just beneath the surface of simplicity. Consider a gentle visualization. Imagine an infinite series of population lines, each representing a different initial condition. As generations progress, lines diverge, intertwine, and form intricate webs. Chaotic trajectories fill the space densely, yet structured branches of periodic behavior persist, forming islands of order amidst turbulence. The picture is simultaneously precise, unpredictable, and quietly mesmerizing. Philosophically, the logistic map teaches humility. Even with complete knowledge of the governing rule, precise long-term prediction may be impossible. Sensitivity to initial conditions reminds us that uncertainty is inherent, and yet understanding the structure provides insight and calm. The journey through the map is a meditation on complexity, balance, and observation. Take a slow breath and imagine adjusting the growth rate slowly from calm stability into turbulent chaos. Observe the branching, the splitting, and the eventual entanglement of trajectories. The process is deliberate, gradual, and meditative. Even as the system becomes unpredictable, the underlying arithmetic remains gentle, precise, and continuous. The logistic map also demonstrates universality. Patterns of period doubling and chaos appear in countless systems, from dripping faucets to electronic circuits, from chemical oscillations to climate models. This universal behavior is a quiet testament to the interconnectedness of mathematics, nature, and observation. Simple rules applied repeatedly reveal the same intricate structures across diverse phenomena. Reflect for a moment on the interplay of determinism and unpredictability. The logistic map shows that chaos is not randomness, nor is it disorder. It is a structured unpredictability, arising systematically from repetition of a simple formula. Each generation is fully determined, yet outcomes are sensitive, intricate, and endlessly fascinating. From a meditative perspective, follow a single trajectory as it evolves. Observe the gentle oscillations, the branching periods, the sudden divergence. Each step is predictable in principle, yet the overall path exhibits beauty, complexity, and subtlety. The logistic map is a quiet reminder that even the simplest processes can harbor infinite surprises. In essence, the chaos logistic segment is a reflection on order, unpredictability, and the hidden depth of repetition. It demonstrates that complexity arises naturally from simplicity, that sensitivity transforms small differences into intricate patterns, and that mathematics can reveal both structure and wonder. As you reflect, imagine the population fraction oscillating and branching, growing and diverging, forming an infinite landscape of calm, intricate chaos. The logistic map is both a gentle meditation and a profound lesson that deterministic rules applied quietly and systematically can produce a universe of endless complexity, beauty, and subtle insight. The game theory segment begins with a quiet realization. Decision-making is rarely isolated. Every choice we make is influenced by the choices of others, and the outcomes we experience depend not only on our own actions, but on the interplay of strategies across multiple agents. Game theory, a branch of mathematics and economics, provides a framework to explore these interactions systematically, revealing hidden structures, patterns, and insights about human behavior, nature, and even abstract systems. At its core, game theory studies strategic situations called games, where individuals or entities, called players, make choices to maximize their own payoff. Spoken in words, a payoff is a measure of benefit, utility, or reward, which may depend on what others do. The framework encourages a gentle reflection on interconnectedness. No player exists in isolation. Each decision ripples through the system, influencing outcomes for all participants. Consider a simple example: the prisoner's dilemma. Imagine two individuals accused of a crime, interrogated separately. Each can either cooperate with the other by remaining silent or betray the other by confessing. If both cooperate, they receive a mild penalty. If one betrays while the other cooperates, the betrayer goes free while the cooperator receives a harsh penalty. If both betray, they both face moderate punishment. Spoken aloud, this sets up a tension between self-interest and collective benefit. Each player must anticipate the other's action to optimize their own outcome. Take a slow moment to visualize this. Picture two people in separate rooms facing a choice. Their fates are intertwined, yet hidden from one another. The outcomes are clear: cooperate and share a light penalty, betray for potential freedom at the risk of punishment, or both betray and settle for mutual compromise. The scenario demonstrates how rational choices in isolation can produce results that are paradoxically worse than if cooperation were possible. A quiet meditation on the subtle consequences of interdependence. From this simple illustration, we see the broader principle of Nash equilibrium, named after John Forbes Nash. A Nash equilibrium is a set of strategies where no player can improve their outcome by changing their own choice, given the choices of the others. Spoken in words, it is a state of balance. Everyone's decision is optimal relative to the decisions of the rest. Even if the result is not globally optimal, each individual acts rationally, and no unilateral change yields benefit. Consider a second example: the coordination game. Two players wish to meet at a location but cannot communicate. Each must choose independently between two options. If both choose the same location, they succeed. If not, they fail. There are two equilibria in this game, reflecting the fact that multiple stable solutions can exist, each dependent on shared expectations. The elegance of game theory is that it provides a systematic way to identify these solutions and understand their implications. Game theory also extends to mixed strategies. In some situations, deterministic choices fail to achieve equilibrium. Instead, players adopt probabilistic strategies, choosing actions with certain probabilities to maximize expected payoff. Spoken in words, this introduces a quiet, subtle layer of unpredictability, ensuring flexibility and adaptability. Even in randomness, there is structure, a methodical balance between risk and reward. Take a moment to imagine a real-world scenario. A group of competing companies setting prices for a similar product. Each firm must anticipate competitors' pricing, customer demand, and market dynamics. Price too high, and sales drop. Price too low, and profits shrink. Each decision depends on the expected strategies of others. Game theory formalizes this interplay, allowing participants to navigate complex, interdependent environments with calm rationality. Beyond economics, game theory illuminates biological systems. Consider evolutionary game theory, where strategies correspond to behaviors rather than conscious choices. Populations of organisms adopt strategies, fight, flee, cooperate, or compete, that evolve over generations according to reproductive success. The payoff becomes fitness, and Nash equilibria describes stable strategies that persist. Even in nature, the principles of game theory quietly govern outcomes, balance, and adaptation. The theory also encompasses zero-sum games where one player's gain is another's loss, and non-zero-sum games where cooperation can lead to mutually beneficial outcomes. This distinction is subtle yet profound. It shapes understanding of conflict, negotiation, diplomacy, and resource allocation, revealing that interdependence can produce both tension and harmony, competition and collaboration. Take another visualization. A chessboard. Each piece moves according to strict rules, yet each player's strategy depends on anticipating the opponent's moves. Every choice has consequences, cascading across future possibilities. Game theory abstracts this dynamic into a mathematical framework, allowing careful analysis of strategy, equilibrium, and optimal behavior. Philosophically, game theory invites reflection on human behavior. Rationality, prediction, and strategic thinking coexist with unpredictability, miscommunication, and adaptation. Simple rules, repeated interactions, and probabilistic choices generate rich outcomes, from stable equilibria to chaotic fluctuations. The framework mirrors life itself, interconnected, responsive, and full of subtle dependencies. Consider repeated games where interactions occur over multiple rounds. Cooperation can emerge even in settings that are superficially competitive, through strategies like tit-for-tat, where players mirror previous actions. Over time, trust, reputation, and reciprocity influence outcomes, producing patterns of behavior that are emergent, dynamic, and quiet in their complexity. Take a slow breath and imagine a network of players, each making choices based on observations of the others. Strategies shift, adapt, and respond. Some players cooperate, some compete, and patterns emerge organically. Over time, equilibrium states form. But the path there is rich, subtle, and full of intricate interconnections. Game theory captures this gentle dance between individual and collective behavior. Mathematically, payoffs can be represented in matrices, showing outcomes for each combination of strategies. Each cell in the matrix is a calm snapshot of consequence, revealing the underlying structure of the interaction. By analyzing these matrices, one identifies equilibria, dominant strategies, and opportunities for coordination or competition. Even in large, complex systems, the principles hold. Markets, ecosystems, social networks, and political dynamics all exhibit game-theoretic patterns. Each agent's choices are interdependent, yet collectively they produce predictable structures, emergent cooperation, or persistent conflict. Game theory provides a lens to observe and understand these phenomena with calm clarity. From a reflective perspective, game theory teaches patience and observation. Understanding strategy requires considering not only immediate outcomes, but the broader network of interactions. Small changes ripple through the system, producing consequences that are subtle, sometimes surprising, and often enlightening. Imagine a quiet room where players sit around a table, each weighing options carefully, considering the reactions of others. Every move carries significance, yet the underlying rules remain constant. The patterns of interaction emerge gently, revealing equilibria, oscillations, and opportunities for collaboration or gain. Ultimately, the study of game theory blends mathematics, strategy, and philosophy. It shows that even in competitive or complex environments, there is structure, balance, and order. Each player's rational choices, probabilistic decisions, and interdependent actions contribute to a rich, quiet tapestry of outcomes. As you reflect, imagine the network of interactions unfolding slowly, each choice influencing another, each strategy revealing subtle consequences. Game theory is both analytical and meditative, a gentle exploration of interdependence, decision-making, and the hidden order beneath the surface of strategic behavior. It reminds us that even in apparent competition, there is structure, insight, and quiet mathematical elegance.